So, welcome all. My name is Luca Corallo. I perform my PhD at Ghent University under the supervision of Professor Patricio Verleisen, and I'm currently a postdoctoral researcher at the University of Catania. And today I have the pleasure to share with you results on my PhD thesis entitled Experimental Characterization and Numerical Modeling of the Plastic Deformation of Ti6 Aluminum 4 Vanadium for high-speed sheet metal forming applications. So, such a long title. Therefore, before to get started, I would like to give a bit of motivation, introduction on high-speed sheet metal forming. So, sheet metal forming is a widely diffused manufacturing technique to produce metal components starting from a relatively thin sheet of metal. And this technique finds application in numerous fields, such as automotive, naval, aeronautics, etc. Sheet metal forming counts of two main parts. The first one more related to the process parameters, and the second one more related to the material behavior. And in my specific case, I investigated the material behavior, including flow curve, anisotropy, and strain rate related effects in Ti6 for vanadium. So in the forming community, formability is often assessed by means of the forming limit diagram, in which the measured strain is reported versus the minor strain. And points in this diagram can be obtained experimentally by performing mechanical tests for monotonic strain path. The area below the diagram represents the region where the sample can be deformed without the onset of plastic strain localization. Therefore, is also said a safe region, while the area above the diagram is the area where eventually plastic strain localization and failure are likely to occur. But the question is, why at high speed? Well, there are studies proving that for some classes of material, at least, an increment of the deformation speed can result in an enhancement of the material formability. And this leads me to the main aim of my research, which is the investigation of the high-speed deformation of Ti6-4 in the formation area of interest for high-speed forming. And the way I addressed this main objective, this main point, is by the following objectives. So, material characterization, development of a novel high-speed forming experiment, material modeling, investigation of the plastic strain localization phenomena extremely important for forming, and prediction of the high strain rate deformation of Ti6 aluminum 4 vanadium. So I would like to begin with one of the main outcomes of my research, which is the development of a new high-speed forming experiment. In this graph, what you see is the projection in the sigma 1, sigma 2 plane of the yield surface and the experiments that can be performed in order to characterize the material anisotropy. And by the time I started my PhD at Ghent University, we could already perform quasi-static and dynamic tensile, compression, and in-plane shear experiments. However, we were still missing an important region of stress states, which is the equibiaxial one, tensile one, which eventually can be determined by hydraulic bulge test. Hydraulic bulge test also allows to characterize the material behavior up to large level of plastic strain compared to classical tensile test, and also allows to identify the material response in a very interesting domain for both formability and plasticity, which is the equibiaxial tensile one. However, there was not yet a well-established dynamic counterpart for this technique. And for well-established dynamic counterpart, I mean an experimental technique able to impose dynamic equibiaxial tensile load to sheet metal and at the same time allowing for the implementation of full-field optical measurements at the sample surface throughout the experiment. So at the initial stage of the designing process, I went through the literature and then I found really inspiring works as the dynamic bulge test, the dynamic Nakajima test, explosive bulge test, and many more. In my specific case, I wanted to combine the hydraulic bulge test with the classical split Hopkinson pressure bar. However, as you can imagine, just placing the hydraulic chamber in between the two bars will not solve the problem. Indeed, the sample surface will be hidden by the hydraulic chamber and by the output bar. So we will not have space for the implementation of optical measurements. Therefore, I solved this challenge, let's say, by the special configuration of the bars in my setup. Here you see the input bar, the hydraulic chamber at the end of the input bar with a sample solidly clamped to an output bar, which actually in this case is a tube, and the input bar is inserted within the tube. This configuration, of course, leaves the sample surface accessible for all of the duration of the experiment, and we can implement DSC measurements, for instance. And here are a few pictures of my setup currently installed at Ghent University. But how it works? So during an experiment, the incident wave travels in the input bar. The input bar dynamically pushes the piston. The piston pressurizes the water, which deforms the sample. The sample is solidly clamped to the output tube. Therefore, the dynamic load is transferred to the output tube. By the synergic combination of strain gauge measurements on the tube and DSC measurement at the sample surface, it's possible to compute the pressure versus out-of-plane displacement at the sample apex, as well as the displacement at each single point at the sample surface throughout the experiment. So once I finished with the development of my setup, and I was, let's say, very happy with that, I could focus on the material characterization. I perform experiment for different stress states, tensile along different direction in the plane of the sheet, in plane shear experiment, and compression test for 3 different strain rates, from the quasi-static to the dynamic loading regime. Tensile experiments put into evidence the strong anisotropic behavior of this material, as well as a drop in Langford coefficient with respect to strain rate. In plane shear test revealed a saturation of the strain rate amplification on the yield stress of the material, while compression experiments on stacked samples clearly indicated the fact that this material is not governed by classical Mises plasticity. Giving a bit more results and details on the material anisotropy, here you see the evolution of the Langford coefficient, also called R value, in the plane of the sheet, as well as of the yield stress in the plane of the sheet, and the remarkable drop in Langford coefficient with strain rate. So these results puzzled me quite a lot and pushed me and gave me a bit of motivation also to look more into the details of the material microstructure. So I perform my texture measurements on the initial sample as well as on the rolling direction and transverse direction sample deformed at quasi-static and dynamic loading regime. So we didn't not observe any remarkable variation in texture, with the only exception of the TD sample, the transverse direction sample, deformed at high speed. In this case, what we observed was a reorientation of the grains accordingly to the loading direction along the transverse direction. And this reorientation of the grains eventually can explain also the change in Langford coefficient. Another interesting result is about the plastic strain localization, so the formation of necking bands in the sample. And we observed that by changing the loading direction, we would get different localization phenomena. Here, I summarize the 3 different scenarios we observed: 2 necking bands equally inclined, 1 necking band contour clockwise oriented, and 1 necking band contour clockwise oriented. And it was exactly here that we realized actually how important and essential was material modeling in order to get a better understanding on this phenomena. So let me introduce the modeling framework I went through. So since this material is clearly not governed by Mises plasticity, I used the yield criterion proposed by Professor Kazaku and Professor Bolatti in 2001, in which the yield function is expressed in terms of J2 and J3, being the second and the third generalized invariants of the stress tensor, Cauchy stress tensor. I use isotropic hardening combined with the multiplicative terms of the Johnson-Cook model, accounting for both strain rate and temperature sensitivities. I assume associate flow rule, and then I implemented the material model in a DYMAT subroutine for Abaqus explicit. On the right-hand side, you see the analytical prediction of the yield criterion with respect to the tensile data at high speed and the good correlation with the experimental data, and the schematic representation of the finite element model as well. This work was performed during my research stay at the University of Florida, where I worked under the supervision of Professor Oana Kazaku. So going to the results, I first performed an overall validation, let's say. So I compared the transmitted wave from the experiment with the transmitted wave from the simulation, and also a more local validation. So the true stress, true plastic strain from the experiment and from the simulation. And afterwards, I look at the deformation history at the sample gauge length. And what we observed is that the model was able to predict the overall deformation. Here you see the ST measurement and finite element results. But we were not only able to predict the overall deformation for different loading direction, but also the three different localized necking scenario that I showed you before. Two necking bands almost equally inclined, one necking band clockwise oriented, and one necking band contour clockwise oriented. And we were quite surprised with these results. Indeed, in the case of plastic strain localization, very often in finite element, it's common use to introduce a persisting defect in the material mesh, such as a groove or a row of softened materials in order to trigger the plastic strain localization wherever you want to happen. But we shown actually that at least for this material is not necessary, and just plugging in, correctly modeling the intrinsic anisotropic behavior of the material, it's possible to predict such a complex phenomena as the plastic strain localization. And finally, going to the prediction of the deformation of this material, this titanium alloy during high-speed forming experiment, I identified the anisotropic model for three different datasets: quasi-static, intermediate, and dynamic data. And here you see also the change in the yield surface for high strain rate experiment. And this change is, of course, in order to accommodate for the drop in Langford coefficient. And on the right-hand side, a schematic representation of the finite element model. Again, global prediction first, pressure versus out-of-plane displacement at the sample apex, as well as the displacement along the sample diameter at different stages of the experiment. And afterwards, a local prediction, local correlation between finite element experiment, the strain and the strain rate along rolling direction, transverse direction at the sample apex. What we observed is that when quasi-static and intermediate data were used to identify the anisotropic parameters, then we obtained the best prediction. On the contrary, the worst prediction was obtained using dynamic data for the identification of the anisotropic parameters. In particular, what we obtain is an overestimation, an overshooting of the experimental data. And this was also clear by looking at the contour plot of the strain field from finite element and from experiment for the three different data set, quasi-static, intermediate, and dynamic. And of course, this comparison was only possible thanks to the possibility to have access at the sample surface throughout the experiment. And this leads me to the conclusion. So another high-speed bulge facility was designed and built to study the dynamic biaxial deformation of sheet metals, allowing full-field optical measurement at the sample surface during the entire experiment. The anisotropic strain rate-dependent plastic behavior of Ti6 aluminum 4 vanadium has been characterized under different stress states and at strain rates, ranging from quasi-static to dynamic. Experimental results and finite element simulation highlighted and confirmed the intrinsic effect of anisotropy on the plastic strain localization phenomena. And finally, the anisotropic yield criterion CP2001 was successfully used to predict the dynamic deformation of Ti6 aluminum 4 vanadium under uniaxial tension, as well as during high-speed bulge testing. At the end of this presentation, I would like to acknowledge the references that I used in my presentation, as well highlighting the main outcomes of my PhD thesis, my PhD work and research. And of course, I would like to thank the funding institution FWO, my supervisor, Professor Patricia Verleisen, for the help, support, and trust throughout the journey of my PhD, and of course, all of you for your attention. Thank you.